everyone, welcome to today's training. This is regarding redesigning and optimizing parts for selective laser melting. My name is Benjamin and I am a design engineer from Materialize. And this training today is a comprehensive training which is divided into two parts. So the first part is about overcome design challenges in SLM. We will talk about process-related stresses mainly today, but also other topics are discussed in further trainings. So I will first of all start with why process-related stresses are even appearing and what can we do about them design-wise. Other than that, I will talk about self-supporting angles and overhang. So why do we even need support in the part and what can we print without support? Also, minimum wall thicknesses and gap sizes and channels will be discussed. There are certain limitations regarding wall thicknesses and the diameter of channels, as well as there are for gap sizes. As the next point, we have the orientation that is not directly a design, a design topic, but it directly influences the design and vice versa. So also the design influences the orientation that we use afterwards for printing. And the orientation also influences the material properties and the surface. So is the accuracy, and the size limitations are mainly due to the machine itself, but the preparation for post-processing is also, dependent on the manufacturing process that's used afterwards, and we have to prepare the part for those processes. And mastering all these challenges, we will go on to the next parts and the next half of the presentation, which is tackling a practical example where we can use our previously gained knowledge. And this is the FEA-based design approach that we can see here. And we can see in the picture at the top right that there is a conventionally manufactured part consisting out of two sheet metal parts and a pin that are welded together. And I did a redesign and optimization of it, and created the part below that, which has a higher stiffness, better printability, so more parts fitting on the build platform, as well a higher safety factor, and also on top of that a weight reduction achieved. And I will guide you through this how you can achieve a part that is as good as this by telling you how to set up a load case for this conventional part, getting an indication of the optimal shape, and with this creating a concept for designing a new part that fits the requirements for 3D printing while respecting all the restrictions, and also thinking about the cost drivers that we have in AM that are different for conventional machining. So, and we always want to utilize every freedom that we have in AM, and I think you can see this as well in the redesign part. So when this is all clarified, we will go into the design flow and I tell you step by step how to design such a part. So to begin with the process-related stresses, or the stress defects which they lead to, we see at the top right a picture of the selective laser melting process itself, having a part scanned by a laser beam in a chessboard pattern or with a chessboard strategy. You can see that there are sparks coming off, so we melt this material really, so there's a very high temperature difference between the molten material and the material surrounding it. So we have shrinkage stresses in the part that can lead to a failure, like you can see at the bottom right picture. So, and as I said, the shrinkage will tear off the support and we can have a failure inside of the part itself or the build job itself. And due to this part coming out of the powder bed, it can collide with a recoater and damaging the machine, and the whole build fails. And now, the ones of you are already into the selective laser melting process a little bit deeper, could say, why don't we use a soft recoater that would not directly collide with the parts sticking out of the powder? And for those, I can say we have the same problem, because the recoater comes over the part that sticks out of the printing bed and distributes the powder unevenly because of this part sticking out of there. So this can also lead to failure. But we want to really understand why these stresses appear and how these stresses appear in order that we can take countermeasures for it. And therefore we will dive into the origin of residual stresses. And at the bottom, you can see there's a schematic picture of a section of a part that is now melted by the laser beam, which acts as a heat source. And you can see that the material is rapidly heated locally, and therefore we have material strength going down at this very heated spot and the material volume increasing there. And therefore we have material compression, because this material which is surrounding that hot spot is has a much higher strength because it's not that warm. And therefore the material tries to expand, but gets restricted by the surrounding material and gets therefore compressed. So we have an elastic and a plastic compression. And therefore, when the part is cooling down, this volume is now also decreasing, and therefore we have thermally induced tensile stresses, because it tries to tear this previously filled material together. And therefore we can see that there's also a momentum pulling on all these layers at once. And this can lead then to cracks in every kind of the every spot of the part, and also delamination between the layers, or support failure, what I've already talked to you about. So now we can better understand how this line that I've shown you previously in the part is appearing. So as I said, we have these thermally induced stresses, and those leading to the part tearing up from the support. And I can show you in a schematic drawing. Let me show you this while using the laser pointer, that we have the support right here, which is resembled by this one, and the layer having shrinkage forces and stresses pulling inward and pulling upward. And you can see that the connection between the part and the support fails, and the part tears off from the support. Then the next layer comes and is printed right where it should be printed, and then a small edge is forming because of the displacement of the previous layer. So, and then we can see it right here in the part. Here is where the support tore off and the part moved upward and inside of the next layer. So now that we know how these stress lines or these stress defects appear, we want to know what geometries amplify those stresses and how can we take countermeasures for it. So let's say we have this part, so this conventionally manufactured part from the start, and would print it like this orientation, and you can directly see this surface at the bottom, we have to support it very heavily. And we know that when there's a large cross section, we have very high tensile residual stresses, and therefore the chance is very high that this part would rip up from the support. So when we can see this directly in parts like this. Even this part is very heavily supported. This high cross section leads to a cracking inside of the part and tearing off from the support itself. So we always want to avoid large unsupported or supported cross sections, because the amplification of stresses in these areas is simply too high. So and this is the same for larger cross sections that are directly connected to the build platform, but also for smaller cross sections, we always try to have a firm connection. And I will show you by using the laser pointer again. This blue radius that you can see here that comes from the part to the build platform, so it's in between them, reduces the notch effect that will increase stresses at very sharp edges. So we always try to have a smooth connection or smooth transition between the build platform and the part. And this is even more so for parts that have a very large cross section from the start, always adding a base with a radius that reduces those stresses. And you can see on the right that there's a crack appearing with parts that have a high cross section from the start without having a smooth transition between the platform and the pod itself. So, and I think we will end this training at this point, and I still thank you for joining the session. And if you want to see more of this training, please don't hesitate to reach out to our experts at the contact address, and you will find this at the end of this feed. Thank you.